when you talk about the lines in Rn, we talk about the equation like this, where A and B some elements of Rn, A and B some elements of Rn. In fact, A has a special meaning. In fact, A is a position vector. It's a position vector. It's a position vector for some point A. The reason for this particular attachment, well, for this particular branding of this equation, it's a line. So every time I look at the equation like this, and lambda here is some real number. Lambda here is some real number. Every time you look at the equation like this, it's a line, and you should be able to recognize a line here. The reason for that is explained here. The reason for that is here. On this diagram, I pictured you position vector for the point A. That's my point A. That's the position vector associated with that. This is a point B, which I specifically based on the tip of the vector A, like this. And you see what happens when you scale your B vector, you will end up with different stretching or shrinking of this B vector. And every time you add this vector to the A vector, you will end up, the vector you come up with, it will be the tip of that vector will be somewhere on this line. In fact, I have this demonstration. Oh, it's not a demonstration if I remove this. Here we go. It's a few position vectors, these X vectors, these red vectors, that's a different X vectors for different lambda value. For instance, if your lambda is 0, you will end up exactly here. If your lambda is 1, you will end up exactly here. If your lambda goes away from 1, for instance 2, you have to double the length of this B, and you will end up here. When your lambda is negative 1, sorry, you have to take the opposite of B, and you will end up somewhere here. The other vectors which you see, they are produced with a stepping point 2, I think. And that's the reason why this equation is called the equation of a line. And you can specify this. In fact, that's the parametric equation of line. And you can also specify this by saying through vector A parallel to the vector B. Nothing terribly difficult here, just something, piece of the definition, piece of the concept which you have to remember. And that's the picture which demonstrates that concept. The other way how you may probably see a line in this course very often is that when you look at the equation like this, and I'll have it here somewhere. Yeah, I'll zoom out a little bit now. It's the other way how you can look at the line. It will be again a parametric equation of the line, but in slightly different form. Is like this. If you're given two vectors now, A0 and A1 in Rn, if you're given two vectors, A0 and A1 in Rn, and both of them are position vectors. Remember, position vectors are those which originate. Position vectors are those which originate from the origin. So it's a two position vectors for 2 points, like in here. So here's my position vector for the point A0. That's the position vector of the point A1. You might see the equation of this form then. X equal 1 take lambda times the A0 vector and the lambda times A1 vector. That's the other form in which the equations appears very often. And that's also the equation of the line. Although the geometric connection with the given vectors, it's slightly different. This is a line which goes through the tips of the A0 and A1 vector. This was the line which goes through the tip of the A vector parallel to B vector. This one is the one which goes through the tips of A0 and A1. Two different forms. Essentially, this is identical forms, but it's easier. It's better for many examples to keep these two forms separate. And again, I can give you this demonstration if I uncomment this trace line thing. Here's my demonstration. So when your parameter lambda varies, take different values, your position vector x will trace with its tip this whole line. And it's also good to remember the areas or subsections of this line which correspond to different intervals of lambda value. For instance, lambda value between 0 and 1 correspond to the segment between A0 and A1. effectively, actually, lambda being exactly 1/2 will be exactly the midpoint of this segment. The values lambda equal 1 is the A1 tip, and the values bigger than 1 will be the half line stretching beyond the A1 to the right. This value will be the value which corresponds lambda equals 0, and the values less than 0 will correspond to this stretching, this half line to the left. Very easy. It's just the two concepts and the geometrical representation for these two concepts which you have to keep in mind. There are two examples, simple examples in your lecture notes, and I put them quickly here. On page 18 they are. On page 18 they are. The first one says we're given 2 points. We're given 2 points like this. No, it says we're given 2 vectors. In fact, vector A and vector B. We're given these 2 vectors, A and B, and we have to produce a parametric equation of a line which goes to the tip of this point and parallel to the vector B. Nothing can be easier than this example. All you have to do, you have to sub your vectors in here and just write this equation as it is. So all I do, I just say x equal, and that's the answer to it. Yeah, wow. Well, but actually, you know, wow wouldn't be more appropriate when we discuss complex numbers, you know. Yeah, but that, trust me, your wow will come. I mean, when it's just like it will come. When I first saw this trick, when you look at the complex numbers as vectors, I was in shock for a week. But your shock will come too soon, maybe. Well, maybe I ruined it for you. Who knows? Because you now know a little bit about it. Anyway, you can of course bring this to the like a per component form. If you can do that, it's nice. So if I bring it to the per component form, that's how it will be, right? The first component 2 plus lambda, second component -3 plus 6 lambda, and last component 5 take 4 lambda. That's the answer they expect from you. 2 lines and that's it. There's another example on page 18. There's another example on page 18, second one, of the similar difficulty, which means nothing at all there. It's just this time you're given 2 vectors. This time you're given 2 position vectors like this, A0 and A1. 2 position vectors like this, and you have to produce a line which goes through the tips of these 2 position vectors. Again, nothing horribly difficult here. All you have to do, you have to sub these vectors into this equation and possibly just do some little arithmetic involved there. So all I do, I just multiply this by 1 take lambda, I multiply this by lambda, and I call this my parametric equation of my line. That's all they expect from you. You can do the arithmetic, of course. You can say x equal, when you do the first component arithmetic, I'm not going to comment on that. It's elementary arithmetic. That's the result for the first component. That's the result for the second component, and that's the result for the last component. And that's all there is to this example. We have another 2 minutes, so probably we can comment on another way we'll look at. When you look at the lines, when you look on lines in Rn, so one way of looking at lines is via parametric equation like this, or via parametric equation like this, depending on the setting, tip of the vector and the parallel vector, or 2 tips for which the line goes. You can also produce a Cartesian equation for the line. And sometimes the Cartesian is more effective than parametric, sometimes parametric is more effective than Cartesian. The connection between these two, it's easy connection, and I'll demonstrate this connection here.